Welcome to Fuzzy Mathematics, the basics. In the previous lectures, we have shown that there are two equivalent definitions of lattices. A lattice is a poset in which every pair of elements has both a supremum and an infimum. A lattice is also an algebraic structure with two binary operations which obey the commutative laws, the associative laws, and the absorption laws. The relationship between the partial order and the two binary operations in a lattice is as follows. A is less than or equal to B if and only if the join of A and B equals B, if and only if the mean of A and B equals A. The supremum of A and B equals the join of A and B. The infimum of A and B equals the mean of A and B. In this lecture, we are going to talk about several different lattices, such as distributive lattices, bounded lattices, complemented lattices, and Boolean algebras. And we will switch between the two definitions of lattices according to the needs. First, distributive lattices. A lattice is called distributive if the two binary operations obey the distributive laws, that is, join distribute over meet, meet distribute over join. Next, bounded lattices. A lattice is bounded if it has a greatest element and a least element. An element in a poset is called the greatest element if it is greater than any other elements in the poset. An element in a poset is called the least element if it is less than any other elements in the poset. We use 1 to denote the greatest element. A is less than or equal to 1 for all A. And we use 0 to denote the least element. 0 is less than or equal to A for all A. Next, a theorem, theorem 1. Let the lattice be a bounded lattice, the greatest element denoted by 1, and the least element denoted by 0. Then, 0 is less than or equal to A, less than or equal to 1. The join of A and 1 equals 1. The mean of A and 1 equals 0. The join of A and 0 equals A. The mean of A and 1 equals A. What's the name of these two equalities? Domination laws. What's the name of these two equalities? Identity laws. Using the definition of the bounded lattice, together with the definitions of the greatest element and the least element, it is easy to see that 0 is less than or equal to A, less than or equal to 1. Now we will prove the rest of the equalities. By the relationship of the partial order and the two binary operations, we have A is less than or equal to 1 if and only if the join of A and 1 equals 1, if and only if the mean of A and 1 equals A. And 0 is less than or equal to A, if and only if the join of 0 and A equals A, if and only if the mean of 0 and A equals 0. By the commutativity of the two binary operations, we have the join of 0 and A equals the join of A and 0. The mean of 0 and A equals the mean of A and 0. So, the join of A and 0 equals A. The mean of A and 0 equals 0. This completes the proof. Next, complemented lattices. First, we will introduce the definition of the complement of an element. The complement of an element A of a bounded lattice with the greatest element 1 and the least element 0 is an element B such that the join of A and B equals 1, the measure of A and B equals 0. In other words, the supremum of A and B is 1, and the infimum of A and B is 0. It is easy to see that if B is a complement of element A, then element A is also complement of element B. A lattice is complemented if every element of the lattice has a complement. Let's do an example. Example 1. The universal set is the set with the 5 elements A, B, C, 0, and 1. Determine whether the lattice represented by the following Hesse diagram is complemented. First, determine whether it is a bounded lattice. Does it have a greatest element? Yes. Which element? Element 1. Does it have a least element? Yes. Which element? Element 0. So, it is a bounded lattice. Determine whether each element in the lattice has a complement. There are 5 elements in the lattice. Let's check them one by one. First, the greatest element 1. Does it have a complement? Yes. Which one? 0, the least element. The supremum of 0 and 1 is 1, and the infimum of 0 and 1 is 0. 0 is the complement of 1, and 1 is the complement of 0. Next, element A. Does it have a complement? What about element B? The supremum of A and B is 1, and the infimum of A and B is 0. Therefore, element B is a complement of element A. What about element C? The supremum of A and C is 1, and the infimum of A and C is 0. Therefore, element C is also a complement of element A. Then element A has 2 complements, element B and element C. Similarly, element B also has 2 complements. What are they? Element A and element C. And element C also has 2 complements. What are they? Element A and element B. Because every element of this lattice has at least 1 complement. It is complemented. From this example, we can see that an element may have more than 1 complement, but an element do have a unique complement if the lattice is a Boolean algebra, which will be the main topic in the latter part of this lecture. A lattice is called Boolean algebra if it is complemented lattice together with distributivity. Let's prove the uniqueness of the complement in a Boolean algebra. Theorem 2. Each element in a Boolean algebra has a unique complement. Suppose this is the algebraic structure induced by the lattice. A Boolean algebra is complemented, so it is bounded. Let 1 be the greatest element, and 0 be the least element. Suppose A is an element in L. Suppose both B and C are complements of A. By the definition of complement of an element, we have the join of A and B equals 1, the measure of A and B equals 0, and the join of A and C equals 1, and the measure of A and C equals 0. We will prove that B equals C. First, we will show that the measure of B and C equals B. By the definition of the least element, 0 is the least element. The measure of B and C equals 0 joins the measure of B and C. Replace the 0 with the measure of A and B. As B is the complement of A, the measure of A and B is 0. Using the commutative laws, we have the meet of A and B equals the meet of B and A. Then by the distributive laws, it is going to be B meets the join of A and C. Meet distribute over join. Replace the join of A and C with 1, as C is complement of A. The join of A and C equals 1. By the definition of the greatest element, as 1 is the greatest element, the meet of B and 1 equals B. Now we have shown that the meet of B and C equals B. Next, we will show that the meet of B and C equals C. Again, by the definition of the least element, the meet of B and C equals 0 joins the meet of B and C. Replace the 0 with the meet of A and C. As C is the complement of A, the meet of A and C equals 0. Using the commutative laws, we have the meet of A and C equals the meet of C and A, and the meet of B and C equals the meet of C and B. Then by the distributive laws, it is going to be C meets the join of A and B. Meet distribute over join. Replace the join of A and B with 1, as B is the complement of A. The join of A and B equals 1. By the definition of the greatest element, 1 is the greatest element. The meet of C and 1 equals C. Now we have shown that the meet of B and C equals C. Therefore, B equals C. This completes the proof. This theorem says that each element in a Boolean algebra has a unique complement. Now that each element in a Boolean algebra has a unique complement, we can use this notation to denote the complement of A. Actually, there exist 3 operations in a Boolean algebra, 2 binary operations, the join, the meet, and 1 unary operation, the complementation. So, a Boolean algebra is often denoted by this notation. That's the end of this lecture. Next time, we will continue this topic. Thank you.